Okay, so this is our intro to the first section in chapter 7, 7.1. It's going to be talking about discrete random variables. But before we really get into that, let's kind of sum up what we just did with our craps example. It says rolling dice is an example of a random event. Well, obviously that makes sense because we don't know what outcome we're going to get. We know it could be a 1, 2, 3, or anything up to a 6, and in this case they're all equally likely, but that's not necessarily always going to be the case in a random event. Okay? When we're talking about rolling dice for craps, well, we can record the outcome as the number of wins in one particular case, and what we would want to do is we want to kind of get everybody on the same page, so we use some shorthand notation. So we say X is going to be the number of wins. All right, so we say X is going to be the number of wins, and that's important because we want to always make sure that we define our variables just as if we were in an algebra class. Now, if we only get one win out of 20 games, then, well, what does X equal? X equals 1. If we think about all the possible values that X could take, well, it could be 1, or it could be 7, or it could be 12. In fact, how many different outcomes are there? At first glance, you might think that there are just 20, but in fact, it goes from 0 to 1 to 2 to 3 all the way up to 20, giving us actually 21 separate outcomes here. So we call X, again, X being the number of wins in the first roll of dice and craps, we call X a random variable because its values will vary when the coin tossing is repeated, as we just saw with our example. Now, let's take a step back here and kind of define this idea of random variables here. As it says here, a random variable is a variable whose value is a numerical outcome of a random phenomenon. So rolling dice, or choosing cards, or flipping a coin, okay, or determining the gender of a baby. Okay, all of these are random phenomena. It says the basic units of sampling distributions. What we're talking about here is when we start talking about these random variables and we take these over and over and over and over again, they come up with what's referred to as a sampling distribution, more of a chapter 9 topic, but we're kind of introing it here to get you to begin to understand all the different outcomes that could happen and how likely each of them are. And as it says on the bottom here, we usually denote it by the letters X or Y, but it really could be any letter that you choose. Now, there's two different kinds of random variables. As we can see up here, we have discrete random variables versus continuous random variables. And the difference between them is very, very important to make sure you understand, because how we deal with the probabilities of each one happening is going to be drastically different. The first one is this idea of discrete. And as it says here, discrete means that there are a countable number of possible values. Countable number of possible values. It doesn't have to be integers. In our example with the craps game, the X that we were looking at was the number of wins out of 20 games. Well, that's a countable number because there could be 0, 1, or 2, or 3, or all the way up to 20. In that particular case, that was an integer solution. All of the values that you could take for that random variable had to be integers. But it doesn't have to be that way. And we'll see some examples in just a little bit of ones that are not. An example would be the number of heads when tossing a coin 4 times. Well, you could get 0 heads, or 1 head, or 2 head, or 3 head, or 4 heads, but you can't get 2.567 heads. That doesn't make any sense in this particular example. If you're thinking about a number that would take a decimal answer, well, then you're thinking about not a discrete random variable, but a continuous random variable. And the definition for a continuous random variable is that it takes on all values in a given interval. So, for instance, it could be a situation where you could have any value from, say, 0 through 20, but not just 0, 1, 2, 3, 4. It could be 0, it could be 0.01 or 0.0001 or 0.000001. It could take any value along that given interval, any decimal that would work in there. What you want to be thinking about in a situation like that is a density curve. Now, when we talked about density curves, we said there's a lot of different kinds of density curves. One of the ones we spend a lot of time dealing with is a normal curve. And let's just say, for instance, this normal curve has a mean of 10, and maybe the standard deviation is 5, so it could be 15 there. Okay? Now, along this continuum here, well, we could have a value here at, say, 12.5, or we could have a value out here at, say, 20, but it really could be 19.95 or 19.99999. And we could go anywhere along that number line there at the bottom. And when we talk about the probability of those values there, well, we're talking about the area underneath the curve, okay, which is, again, what we talked about back in Chapter 2 with normal curves, or if you're taking calculus, it's talking about the integral over that interval. An example of something that might be a continuous random variable, well, the time it takes to record your 100-meter dash. Now, you might think of that and say, well, sure, but maybe my time is 11.5 seconds. But we're just rounding it to 11.5. It didn't take exactly 11.5 seconds, at least that's very unlikely. More likely it took 11.54327 seconds. But we always round, or because our stopwatches round to that certain value there. But that doesn't mean it has to be that specific value. What we see here is a more formal look at the discrete random variable. And it says a discrete random variable x has a countable number of possible values. The probability distribution, this being a very, very important phrase, the probability distribution of a discrete random variable x lists the values and their probabilities. And I want to draw your attention to this box right here. It's really going to be more like a table when we set it up, where we have two rows. We have the values of x on the top, and they just call them x sub 1, x sub 2, etc., all the way out to x sub k, and the probability associated with each one of those values. So for this first value, x sub 1, the probability of that occurring is p sub 1. And it goes all the way out until we have accounted for all of the possible outcomes of x. Now, this only works for discrete random variables, because when we talk about discrete random variables, they have to take a countable number of possible values. When we talk about continuous random variables, they can take any value along a range. So if you think about that, well, you can't write a probability distribution, again, probability distribution for that, because it could take an infinite number of values. Now, in order for this to be a true probability distribution, there's two requirements. First is that every probability is a number between 0 and 1. Well, that makes sense because you can't have a negative probability of something occurring, nor can you have a probability of something occurring being higher than 1. Okay? Also, it says that the sum of the probabilities must be 1 because they must account for all possible outcomes in this particular case. And as it says on the bottom, you find the probability of any event by adding the probabilities p of the particular values x that make up the event. And if we think back to Chapter 6, why is that? Well, because these are discrete random variables that are also disjoint. Because disjoint means they don't have any outcomes in common. So if you're looking for the probability that you get 5 wins or 6 wins out of 20 when you're playing craps, well, you can't win 5 and 6 at the same time. So you would add those two probabilities together, and you would find the probability of winning 5 or 6 times in craps. Okay, so let's take a quick look at these examples here. It says identify each below as a discrete or a continuous random variable. At this point, it would be a good time to pause your video and think about each one separately. And then once you have in mind what you think they are, go through the rest of the video here. First one says points scored in a basketball game. Well, you can score 1 point at a time, or 2 points at a time, or 3 points at a time. You can't score 2.567 points at a time. So that tells us that points scored in a basketball game is going to be discrete. Blood alcohol level. Well, your blood alcohol level is a measure of how much alcohol you have in your blood, and it's being measured as a proportion. So that proportion, we'll call it BAC, that has to be, well, it has to be less than 1 because it can't be more than 100% of your blood in your body, and it has to be, well, could be equal to 0, but it can't be less than 0 there. Okay? So if we think about it, it could take any values from 0 to 1. So it could be 0.08, the legal limit, or it could be 0.000567. In that particular case, since it could take any value along that range there, that's going to represent a continuous random variable. Money won on a trip to Las Vegas. Well, you could win $5, you could win negative $30, you could win $20.50. But you can't win 20.501234.6 cents. So even though it's not an integer, it's still still, in this case, going to be a discrete random variable because it has to go up by that increment of at least 1 cent per outcome. Now, is this something that you would probably write into a probability distribution? Well, that would be a pretty difficult thing to do, but theoretically you could. And the last one here, time one can hold their breath. Time one can hold their breath. Well, again, this is just like the running the 100-meter dash example. You might be able to hold your breath for exactly 20 seconds, but more likely than not, it's going to be 20.1275 seconds or something along those lines. So this last one here is going to be continuous again. And one thing you want to be able to keep in mind here is that countable is different than finite. If we think about our example right here, this third one here, the money you win on a trip to Las Vegas, it's countable because it goes up by at least 1 cent. But that doesn't mean it's finite because theoretically speaking, you could win an infinite amount of money there while you're in Las Vegas. Theoretically speaking, not practically, okay? But that could happen. So countable is different than finite, and that's an important concept moving forward. Now, we said probability distributions are really, really important here, okay? And this example here is looking at the number of boys in a 3-child family. So we set up our probability distribution as this. X, which is representing our number of boys. You could have 0, 1, 2, or 3 boys. And what we want to do is we want to find the probability of each one of those examples happening. Now, this might not be something completely inherently clear to you, but if you think about it, if you have 0 boys, well, that means you have 3 girls. So that's where you have a girl, and a girl. Now, girl and a girl and a girl, well, the probability of each one of those happening is 1/2 times a half times a half, which leads us to 1/8, as we see represented right here. Now, the next thing you might want to do is go on ahead to finding 3 boys, which would be obviously boy, boy, boy. And would that probability be any different than finding 3 girls? Obviously not. It's going to be the same probability. So that's also going to be the 1/8. Now, the 2 in the middle, that's where it becomes a little bit more difficult because, well, there's more than one way that that could happen. For instance, if we have 1 boy, well, maybe that boy was the first child born, or maybe it was the second child born, or maybe it was obviously the last child born. Each one of these have a probability of 1/8 occurring, and since there's 3 different ways it could occur, the probability of having 1 boy is going to give us 3/8. 2 boys is going to be the same thing because it's going to be the same diagram as we see here, just with boys replacing with girls. So that's another 3/8, and finally 1/8 here. And that's how I would recommend making this probability histogram, starting with the outsides and then working your way in from there. Now that we have this probability distribution, we should first check, make sure that if we add up all of these probabilities here, they are going to equal to 1, and 1/8 plus 3/8 plus 3/8 plus 1/8 is going to equal 1. So we have accounted for all possible outcomes there, which makes sense. You can't have 4 boys in a 3-child family. Now all we need to do is answer some questions about it. And again, if I were you, I would take a pause and look at each one of these and try to answer them on your own. The first one says the probability that X is less than 2, meaning we have less than 2 boys in this 3-child family. Well, what are the successful outcomes here? Well, you could have 1 or you could have 0 boys. So all you have to do is look at those 2 probabilities and add them together. We get 1/8 plus 3/8 is 4/8, reduces to 1/2. If we look here, the second question looks oddly similar to the first, with the difference being the inequality symbol. Now we're saying less than or equal to 2, which includes one more possible outcome, this example here where we have 2 boys. So all we have to do is add that into what we already had for number 1. 1/8 plus 3/8 plus 3/8 equals 7/8. And there we go. The only one not included there is having 3 boys. Okay? Now, if we were to go one step further and say, well, what if we're tossing 4 coins? Really the same idea as having a boy or a girl, but now we're tossing 4. Okay? I'm not going to take the time to show you out how to find this probability of each one of these occurring, but now you're no longer dealing with 8 possible outcomes, you're dealing with 16, because it's a half times a half times a half, or 2 times 2 times 2 times 2. Probability of having 0 heads But that's 1/16 because it's tails, 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 tails. A half times a half times a half times a half, or a half to the fourth. Keeping going, we go across a fourth, 3/8, 1/4, and 1/16. It'd be a good idea for you to take the time right now to look at that and make sure that that makes sense to you. Don't just inherently trust it, because again, you're going to need to be able to do this on your own. And again, now that we have this probability distribution, you should pause the video and take a look at finding these answers here. The probability of tossing at most 2 heads, well, at most means that you're going to have 0, 1, or 2, so we're just adding those probabilities there. And we see the probability of x equals 0 plus x equals 1 plus x equals 2 gives us 11/16. At least 1 head. Well, at least 1 head means it could be 1 or 2 or 3 or 4, and I could add all those up. But a slightly quicker method would be to just find the probability that it is 0 and subtract that from 1. As we see here, probability that x is greater than or equal to 1 is the same as probability that x is 1 minus the probability that x is less than 1. Okay, that actually right there should not be there. Sorry about that typo. 1 minus probability that x is less than 1, which is really the same thing saying 1 minus probability that p, that the probability of 0, and that's 1 minus 1/16, which is 15/16. Now, once we have that distribution there, again, looking at the probability distribution right here, we can make a histogram to represent it. And that's what we see here. We see the outcomes here, 0, 1, 2, 3, and 4, and the probabilities associated with each one of those. And obviously, getting 2 heads out of 4 is the most likely event, 0 and 4 the least likely events. If we were to describe the distribution, that's going back to really chapter 1. Well, we're talking about shape, center, and spread. The shape, well, that's roughly symmetric, because we could see, if we were to do this, extending it out, we would see that this shape would generally follow that symmetric curve. The center, well, clearly, that's right there too. As far as spread, well, we could have anywhere from 0 to 4 outcomes there, 0 to 4 heads there. So that's our idea of spread. Okay, we'll formalize this more a little bit later in the chapter, but that's kind of where we are for now. Okay, and this last example is getting into more of an application problem. It says, let x be the number of cars that a randomly chosen American household owns. Here's our probability distribution. And again, make sure that phrase is getting ingrained in your head there. We have the x represents the number of cars, where we have 0, 1, 2, 3, 4, or 5. Obviously, in this case, we're ignoring anyone who has more than 5 cars, because that'd be ridiculous. And the probability is associated with each one of those. Clearly, we can see that having 2 cars is the most likely outcome here for a household in America, according to this data here. And again, we could have some questions to answer for this. Pause the video, answer the 2 questions, and then watch the video. First one says probability that x is greater than or equal to 1. Well, greater than or equal to 1 means that it could be 1, or 2, or 3, or 4, or 5. Could we add them up? Sure, we could. Do we have to? No, because we can just take the probability that x is less than 1 and take that away from 1, and we can have our probability that satisfies this problem here, which is what I show here. It's the same as 1 minus probability that x equals 0, which is 0.91. What percent of households have more cars than a standard 2-car garage can hold? Well, it's not written in probability language, but we can make it into probability language to say the probability that x is greater than 2, because that would be greater than a standard 2-car garage. And I show here, writing out the probability language, which is equal to the probability that x equals 3, plus probability that x equals 4, plus probability that x equals 5, and add those probabilities up, because again, they're disjoint events, and there we are, 20%, 0.2. Okay, so what we have here is we've gone through the difference between discrete and continuous random variables. We've talked about discrete random variables, specifically how we go about writing the probability distribution, and how we go about finding probabilities based on certain criteria given. And we have some work up here for you to be working on, 7.2, 3, and 5, all on page 470. Okay, that will be kind of our intro exercises to get ourselves kind of understanding discrete random variables a little bit better. Now let's see if I can figure out how to stop this video.